going to talk about the irrationality of Gushel-Mukai fourfolds.
Thank you very much. And I would like to thank the organizers for inviting me and giving me the possibility to give this talk. And yeah, I'm very happy to be here again in Campinas. So yeah, I will talk about this irrationality of Gushel-Mukai fourfolds. So if you want, this follows the steps of this atom theory that we've been hearing from Leonardo and Jeremy, and it's just a computation in another case, if you want. Well, at first, I guess maybe you don't know what Gushel-Mukai varieties are, or why we should be interested in this. We already saw that with this atom theory we can get some irrationality for cubics, and you should think that this is the brother of so Gushel-Mukais are the other brother, like a brother of cubic fourfolds. So they have similar properties that allow to apply this machinery of atoms. Yeah, there are many things which are similar between cubics and Gushel-Mukais. One, which I will not develop here, is a relation to hypercalorie. Yeah, so for cubics you can you have an hypercolor associated to cubics, and for Gushel-Mukais also you can associate a hypercolor variety, and this is one of the main reasons maybe why they were studied a lot. So let me start with the cubics. So just to freshen your memory. So we want to study this rationality, and well, I guess so we want to understand when we have a rational map between a variety X and the N, so which means that we have there is the open subsets of X and N which are isomorphic, and then okay. So rationality, it's a very tough question. If you want to prove rationality, there are a few techniques only. So it's already difficult, but then you may ask, okay, how does rationality behave in families, if you're very courageous? Not in families, but let's just say that if you have a variety, maybe you understand its rationality, and then you want to deform the complex structure and see if rationality is preserved. And so yeah, if you deform the complex structure, what can you say about rationality? And if you want, you can phrase it in other terms. If you have a moduli space, then you can try to describe the locus where your varieties are rational. And this doesn't work well. I mean, in dimension 1 and 2, if your variety is rational, then you deform it and it will remain rational. But starting from dimension 3, things could change. So the example you should have in mind is cubic fourfolds. So if you want also cubic threefolds, but they're all irrational, so you don't see this phenomenon. So cubic fourfolds, so just you take a degree 3 equation in P5, and you have a moduli space of dimension 20. And the question is, what is the locus of rational cubics? And so just to keep the thing in mind, you have this moduli space of cubics, and the very quite long-standing conjecture was and is still that the rational locus is just a countable union of divisors. Okay, so varieties in here are rational, and then the rest should be irrational. So one point for cubics is that the Hodge structure defines your complex structure. So if you want, you have your hk of the cubic, and then you decompose it as hpq. And this decomposition actually defines your complex structure. So you may So this is reasonable. So if you should look at for cubics at least, you should look at the Hodge structure and try to recover the information about rationality. And that's what Katsarkov, Kontsevich, Pankov, and you managed to do. They use these Hodge properties to show that the very general cubic is irrational. Okay, so just let me say that, as I said, rationality is a difficult problem. So you still have to prove rationality if you want to prove the conjecture for a lot of devices. Okay, so I'm talking about cubics, but this is a Gushel-Mukai talk, and just Gushel-Mukai are similar to cubics. So if you want, if it's one of the first times you hear about both of them, just keep in mind that, well, if you understand Gushel-Mukai, you understand cubics. Okay, so the definition is, okay, you can define it as with some invariants. So Gushel-Mukai variety is a Fano variety of, let's say, dimension n, with Picard rank 1, index n minus 2, and you have this degree 10. But actually, so Gushel for 3 folds and then Mukai for any dimension show that it's always a bunch of hyperplanes intersected with a quadratic section in the Grassmannian 2D5. Okay, so in the case of fourfolds, you just get one hyperplane section. So I mean, X is equal to this thing. So as for cubics, it's a very simple variety, you may think. But there is a lot of geometry behind these varieties. And you can realize that there is a lot of geometry from the odd structure. So the odd structure, maybe, and also this, I will leave it here. You have the odd structure of the Gushel-Mukai is you have something ambient, so like this. So these are the odd numbers. Okay, and something like this. So this part comes from the Grassmannian. You just restrict classes from the Grassmannian. That's the ambient part. And then you look at the vanishing cohomology. So the vanishing cohomology is so it's the kernel of the push forward from the Gushel-Mukai to the Grassmannian.
But you say it's n-fold, and then I think now you fix the dimension.
Yeah.
So it's n.
No. From this line on is fourfold. Yeah. In dimension 6, it's similar Hodge structure, and but in odd dimension, it's rather is a Jacobian. I mean.
But this starts in n equals 4, or is there n?
No. Well, you if you want Fano, it starts n equal 3, 4, 5, 6. 6. Yes. Yeah, 6 you have to take. So these are. So yeah, what I should have said is that these are the ordinary fourfolds. Then you have other Gushel-Mukai for which everything will work pretty much the same. Which are instead of taking the quadratic section, you replace the quadratic section with a double cone. Ramified along. But yeah, so it's only dimension 3, 4, 5, and 6. Rationality is known for dimension higher, bigger or equal than 5. If I'm not wrong. For dimension 3, only let's say very general Gushel-Mukai 3-fold is irrational.
Actually, all of them are.
Yeah. So what I was saying is that I think who should I say?
Well, the theory of atoms shows
Yeah.
that.
Okay. So from the theory of atoms, I haven't seen the argument myself, but one should be able to prove that all the threefolds are irrational, as for cubics, and then you get this fourfolds where things could change. Okay.
Sorry, for a higher dimension, you said it's rational or no?
I don't remember, but for higher dimension, I think the question is no.
5 and 6 are rational. Dimension 5 and 6.
It's okay? Yes, so and again, so as for cubics you have this, so for cubics it was a primitive cohomology, but it's more or less, it plays the role of the
Or the
vanishing
complex
here.
numbers, so we have group action, some interesting phenomena probably.
So this is the Indian part, and this is the vanishing cohomology, and you get this structure, and this is the H2 of a K3 surface. And so we will see that K3 surfaces will appear again. So if you want the odd diamond of a K3, well, I remove the zeros. Okay. Okay. So what I said for cubics is that the Hodge structure determines the complex geometry. It's not true for Gushel-Mukais, but the Hodge structure determines the birational geometry of Gushel-Mukais. So you have a period map. So if you deform the complex structure, of course the differential, the topological structure remains the same. So you can fix this lattice with the vanishing cohomology, and then you can construct the period map. So you have to prove that there exists a moduli space, but for Gushel-Mukai everything works fine, and that it has nice properties. It's irreducible and quasi-projective. And then you get this map. So to a Gushel-Mukai you associate, if you want, the H31 inside. So inside the period domain, so there is a mistake here. So you take the projectivized of this, okay, and then you have these two conditions, just because the H31 satisfies this condition for the intersection, Perrin, and then you have the quotient by the more or less the automorphism of the lattice, and you get this period domain, which is a 20-dimensional manifold, as for cubics. So the picture is we will see that there are also some devices here, interesting ones. And so what I was saying is that so if you the dimension of the moduli space of Gushel-Mukai is 24, so it's not 20, but the fibers of the morphism are all birational. So if you want to understand the birational geometry of Gushel-Mukai, you can parameterize Gushel-Mukais with the period domain. Okay. This was proved by Debar and Kuznetsov. Okay. Okay. So now you try to understand a little bit of this moduli space, how to construct these devices, some devices. And what you can do, so the first thing you notice is that if you take a very general Gushel-Mukai, the Hodge classes will just be the classes that come from the Grassmannian. So in general, you will have this property. So the Hodge classes will be classes coming from the Grassmannian, which we know are algebraic always. And then you have the orthogonal to H31 and H13. And so if you want, as your point W moves in this space, you can get different Hodge classes. And this is the motivation for the following definition. So roughly, let's say you have to be a little bit more precise, but you can take an element in your lattice and look at the following space in the period domain, you just look at all the classes that are orthogonal to alpha. And so if they are orthogonal to alpha, let's say if W is orthogonal to alpha, then alpha will be a Hodge class. Okay, but since it's in lambda, and lambda is in the vanishing cohomology, you will get an extra Hodge class. Okay, this is everything works like for cubics. So these divisors actually they are identified by the discriminant of the orthogonal lattice of alpha. I should use this. Okay. And you define so Gushel-Mukai would be Hodge special if you have some extra class, if you want, in the Hodge class. So if the image of the Gushel-Mukai is in this union of a countable union of divisors. Okay, and of course you would say Hodge general, which means very general, if it's not over there. So very well. And
the expectation is that these Hodge specials are all rational.
No. So the Ilep and Manivel they show that you have this D is non-empty if you have these two conditions, and it's irreducible in the first case, and there are two irreducible components in the second. And then they also give criterion for when you have a K3. And well, the criterion, maybe it's not really important, but so you have a numerical criterion when you have K3s. And what you ask is that this orthogonal lattice is the primitive lattice of a polarized projected K3 surface. And you have a twist here. Okay. And then the story is a little bit more complicated, but if you want to think about cubics, the divisors where you have the conjecture for cubics is that they are rational when you have this condition. So you may think, okay, maybe you can at least state a conjecture in a similar way. So just let me take one example. I think it's the next slide. You take D equal 10. No, yes, D equal 10, which satisfies this condition. And so of course you try to see if it's true that the behavior is similar to cubics, then you should have this. You should have that Gushel-Mukai and D10 are rational, and this is the case. So just very rapidly, Gushel-Mukai so you have two connected components. Let's just take one. So Gushel-Mukai in one of the connected components has a plane. So these are Gushel-Mukai that contain a plane. So this is the extra algebra class, Hodge class. And from the plane you just project, and the image is a smooth quadric, and it's a rational. It's a rational map, and even you get explicitly the K3. So here, so the blow up at the plane of X is the blow up of the quadric at this K3 tilde, which is itself a blow up of a K3. Okay, so as I already said, we have an example, so now we can state the conjecture. So the conjecture is that the very general Gushel-Mukai fourfold is not rational, and it's rational if and only if there exists an Hodge associated K3 surface. So if the lattice, the orthogonal to alpha, is the lattice of a polarized K3 surface. And the evidence is this D10 I told you about, and then there is also an example in D20. An example. There is also a divisor D20, which was studied by Stagliano. Yeah. So of course, if you have, it's almost tautological. But if you have an isomorphism with a primitive K3, then you have an extra Hodge class. And so X will not be Hodge general, meaning very general. Okay, so this is if you were with cubics, then you would stop here. This is the similar conjecture for cubics, and then you have a derived version, which was stated by Kuznetsov, and the derived version is equivalent to this one. So there exists a derived associated K3. For Gushel-Mukais, you also have a derived version. I will not enter into details. You have derived. So the Gushel-Mukai is rational if and only if the derived associated. So if and only if there exists a derived associated K3. The problem is that these two conjectures are not the same. And if I understand well, so this was Asset telling me this. So probably the second conjecture is more likely to be true. Okay, so
What makes you say that?
because this was because the second conjecture should be reformulated. One should be able to reformulate it in terms of transcendental lattices. So you can say that the transcendental lattice of the Gushel-Mukai is the transcendental lattice of over K3, and while it's not always the case in the first. So two conditions are not the same. And Asel was saying that this is the real condition. This is really the condition I should look at. I asked him the question. But for the moment, only rational Gushel-Mukais are in this. It was here. Are in this D10 and D20. And so here, if you want, this is a divisorial condition, and here you have loci of dimension higher. I don't know. Okay, so the result. So the result is, if you want, similar to the cubic case, so a Hodge general, or which means very general Gushel-Mukai is fourfold. It's not rational, and if it is rational, then there exists a projective K3 and an isomorphism of Hodge structures. So this is exactly similar to what to the result that Jeremy presented yesterday, except that there is this Q bar. So I think. So I'm quite sure, but I wanted to just not to state something wrong, which I already did. So this Q bar actually one can restrict to Q of I, and it's because Iritani put some notes where he says that his blow-up formula works over Q of I, and so maybe I will explain why we cannot get rid of this extension of Q, while Jeremy can. And so we have also something which should appear very soon about northern Gushel-Mukai, which are rational to Beras. We cannot say anything about rationality, and maybe later we can explain to you why, but we can say something about the rational geometry. For example, we can say that these varieties are never birational to a very general cubic. Of course, the rationality problem is the first one you would like to solve, but then you want to understand all the birational models of your varieties, and if you have new varieties in a birational set. Okay.
So the statement is that very general Gushel-Mukai is a singular Gushel-Mukai is not variational to very general, I think.
Yeah, also, yeah. Okay. Okay, so just so yeah, I will try to recall a little bit of the strategy we atoms that we used. So, and then so the plan is I want to explain a little bit of this how we prove this theorem, and actually there is a part which is computation. You want to compute the quantum cohomology of your Gushel-Mukai, and then you want, let's say, apply the machinery of atoms. So maybe I recall this. So you take so we worked with at the beginning with a small quantum cohomology ring. So just think a ring that you can attach to your variety with a quantum product, and with this element here, which is special because it's so the Euler vector field is preserved by Iritani's blow-up formula. And so when you're in the, so here I put small, and for example, if you remember Leonardo Jeremy's talk, there were some variables q and then some variables t, and here, as we will see, we don't have the variables t. So when you don't have variables t, this Euler field is just the C1 of your variety. Then what you do is and this is just computation, you compute the matrix of this quantum multiplication. And you have different methods. So Giovanni explained his GKM method with if you're in flag varieties, or in GKM spaces. You can also use periods, quantum periods. That's not what we did. We just used the geometry for even linear algebra. I don't know. I would say this is old style, but the others are old as well. So okay. So and you compute this matrix, and then you get a bunch of so you get a decomposition of your quantum cohomology in eigenspaces. If you remember, so these are generalized eigenspaces, and then you argue like this: if you have that X is birational to before, then you have a weak factorization Jeremy talked about. So you have a sequence of blow-ups and blow-down. Okay, I shouldn't write like this, but so this is not very precise. Okay, so this is x0, x1, and then you continue. This is not precise. I don't. Okay, and so your generalized this generalized eigenspace, they are preserved by these blow-ups and blow-down. So you should be able to recover them either as some generalized eigenspaces before, either in some blow-up center. Okay, you have this. If you want the formula of the blow-up, the cohomology of the blow-up extends to this decomposition. And of course, here I'm just passing all the details Jeremy talked about. You should define an evaluation map and do things a little bit with care. So I just put the easy version of it. And okay, and so you compute these generalized eigenspaces, and then you focus on the one which contains the H31, because there is no H31 in P4. So as also Jeremy recalled, the Hochschild degree is preserved. So if you have an eigenspace with some H31, you should the generalized eigenspace should appear as an atom of something else. It cannot appear as Pn, so it has to appear as an atom of a blow-up center. And then you compute. So that's why you focus on this eigenspace, and then you compute these invariants. So the first two were already used in KKPY. So this is essentially, this will be 1 if you assume that your eigenspace contains the H31. And what you care about is that it is at least different from 0 at the beginning. And then this is the only invariant that depends on the Hodge classes, so on the complex structure, while the rest is doesn't depend on it. And so I will come back to this, but if you show that these invariants are not the ones that can appear for a surface, then no surface will have this atom, and then you get the irrationality. So you cannot have a sequence of blow-ups and blow-downs that really adds to forward. Okay, so okay. So I don't know if there are questions. So now I want to explain the computation here of this matrix. So maybe this quantum cohomology will not be as exotic as it seems. I hope so. So at least here it's the last chance. So maybe. No, maybe not. Okay. Okay, so just set up. So we want to define this. This small quantum cohomology ring. So which is a deformation of the usual cohomology ring with its intersection pairing. So this is a bullet. So you deform the product, and you deform it by adding a new variable. So in the small quantum cohomology, here you can take just polynomials from this variable, but in general, you should take a series. And okay. And then the quantum product is this one. So you see, if you put Q to 0, then you recover the intersection pairing, and otherwise you have this sum Q to the power D, and then you have these Gromov-Witten invariants here that appear, and the whole point is to compute these. So what are these? So you take the modular space of stable maps from a rational nodal, maybe curve to X. Yeah, not rational, genus 0. Okay, with 3 map points, and you have some conditions. So of course this D here that appears here will be the degree of your curve. When you push forward the class of the curve, and then you have these 3 marked points on your curve, so you can evaluate them, and you get evaluation maps, and then you define. So this already appeared, even with more insertions here, more classes. You do the integral over the virtual fundamental class, so you have to show that it exists, and then it as well, and of the pullback by the evaluation maps of your classes. And so, as Giovanni said, roughly, here you're counting degree D curves passing through sigma prime, and tau. Roughly. So you need to prove that it's exactly, you're counting exactly this, and this is what's called enumerativity. So I will show that in this case you can do it. Okay. So yeah. So let me say another thing. So you want to show enumerativity. So I will show that it's more or less doable. And there is another thing which is you should keep in mind, that is that computing these invariants when there are some classes in the vanishing relative cohomology, there are not many techniques to do it. It's really a tough question. So you want to avoid dealing with the vanishing cohomology. And if you're lucky enough, you can use some monodromy argument. So our varieties, our Gushel-Mukais are so they are complete intersections. So you can see them as a okay, I wrote hypersurfaces, but it's not quite true. If you want, they are hypersurfaces in a hyperplane section of the Gasparian. And then you have this monodromy action, so which, yeah, there are differential geometries. So you just do a full parallel transport of classes. Okay. And if you do parallel transport, since all the varieties are in G25, the ambient classes will not move. Okay, so they will be invariant. And then you get an action of the P1 of your family on the vanishing cohomology. And the very important thing is that this action is irreducible. Okay, so you have an irreducible action, and then you try to use this as much as you can, because it's the only real information you have. But Gromov-Witten invariants are monodromy invariant, they are deformation invariant. So what you do, you have this, so you can prove allele lemmas, but you have this one, which tells you that if you compute a Gromov-Witten invariant where there is only one class in the vanishing cohomology, then this should be 0. And this is, so the reason why this is true is because you see this as an element in the dual. So if I remove tau, this becomes a function of h for x, linear, and since all these classes are ambient, they are monodromy invariant, so it's an invariant element in the dual of this, but this is irreducible, so the only invariant element is here. Okay, then you get the very nice consequences. So the first one is that, so if you take an ambient class and you multiply by other ambient classes, then you remain in the ambient cohomology. You can never go to the vanishing side. If you multiply your ambient class with a vanishing class, then you have to come back to the vanishing homology. And actually, you can even prove that on the vanishing cohomology, you have the multiplication is just multiplication by a multiple of the identity. And the reason why is that you find one eigen vector, and then you move it around again with the monodromy action. So maybe. Yeah, I don't know if I have to come back to this. So you have your E U star, Z star. So this will be a matrix. So you have H ambient and H vanishing. And what this is telling you is that. Okay, and then of course you don't know what things are here. But if you want to find generalized eigenspaces, that this is what you want to do. Okay, and then so the same properties hold if you deform your ambient cohomology. So you add again the t variables that were in Jeremy and Leonardo and Giovanni Stock. But if the deformation is again ambient, then you still get these properties. And the same for the Euler vector fields. So the Euler vector fields, when you deform with an ambient deformation, will be something like this. If alpha is homogeneous, and then you recover the same. Okay. Yeah. What I didn't say is that we worked in the small quantum cohomology, and at a certain point we had to deform. So that's why I'm putting also this information. 10 minutes? Yeah, okay. Okay, so I will just explain this. So okay, you compute the Euler multiplication. So U0, as I said, in the small quantum cohomology. And so the remark is that, so the first remark you will do, since you really don't know anything about the primitive part, is that this lambda is 0 for U0. And this is the fact that the index of your varieties is 2. But if the index is 1, even this fact you don't know. Okay? And then you get this enumerativity property. So since you're focusing only on ambient classes, so recall ambient classes are those that come from the Grassmannian, and in the Grassmannian you can move classes with the UGL5 action. So you can always suppose that the intersection, and even the intersection in the modular space of curves, is transverse. And so you get that. So if your degree is small, and your classes as pullbacks of some classes in the Grassmannian, then you can find some representatives such that this number, in fact, if you take general representatives, then this number, this Gromov-Witten invariant, just counting degree D rational curves passing through some subvarieties. And this is, you can do it by hand. Okay. Okay, so I wanted to explain a computation of at least one of the invariants, but maybe you want to just focus on the last argument. So just to tell you that you can use nice properties of the quantum cohomology, and you reduce. In the end, you have to compute very few Gromov-Witten invariants, and you have to count. So this you have 3 Gromov-Witten invariants at degree 1, so you have to count the number of lines in algebra. And then this is a little bit more complicated. Here you have to deal with conics in your Gushel-Mukai. And essentially, to compute this, what you do is you look at conics in the Grassmannian, and then you try to impose conditions. But yeah, so the lines is very easy, and then you have to do it. So. And then the conic, this is the proof for the conics, condensed. Okay, and then you get this matrix, which is the multiplication. So it's this matrix here. So you restrict to the ambient part, and you get this. Okay, you get this characteristic polynomial, and it has. So you see if you can do computation very fast. That it has 4 eigenvalues different from 0 with multiplicity 1, and then you have an eigenvalue, so 0 with multiplicity 2. So if you look at the kernel, you get this, and actually it is a kernel. Okay, you have a 2-dimensional kernel. So if you look at the kernel, you decompose it as a, so all the vanishing cohomology goes in the kernel of the multiplication plus 2 classes. And these 2, so the fact that here you have just 2 classes is what implies irrationality by KKP1. Okay, we were not satisfied with this because, so if you want, you have in H ambient, so you have here you have alpha and beta. And so the matrix here is, so if you restrict the matrix here, this is just 0. And now if you look at the big quantum cohomology of the K3, and you look at the same operator, it will not be EU0. There is a very famous change of variables Jeremy talked about. But the matrix will be like this. So you have H0, H2, H4, and now we'll get it wrong, certainly. So you will have an eigenvalue, lambda, and then you will have something here. But so something here, so it's in the space generated by H0 and H4. So if you could have also in the case of so you know that this matrix should be conjugated by the, if your Gushel-Mukai is rational, this matrix should we conjugate it to the matrix here. Okay? And of course, so if you just work with a small quantum cohomology, then here you have 0, and you cannot distinguish these 3 subspaces. But if you have something here, and maybe something like lambda, lambda, and then something here, then you can say that this block, so the Jordan block here, should be sent to this block. So that's the reason why we deformed, and we found exactly that the ambient part has a Jordan block, and so we could compute the invariant I was telling you about before. So for the irrationality of the very general, you don't need this deformation. You already get it from these 2 properties. And but for the second result about the cohomology of the K3, you need this to be equal to 1, okay? And you need to know where it is. And well, so the as I said, so your generalized eigenspace should appear as a generalized eigenspace in the cohomology of P4 or a smooth center in some deformation of the cohomology. And so KKBY tell you that if you have this invariant like this, then in lambda is not a generalized eigenspace of surfaces, points, or points, and it's not also a generalized eigenspace of P4. So you cannot, via the weak factorization, you cannot transport it, or it cannot appear in the weak factorization, and then you get irrationality. And if you use Jeremy's argument, then you actually use the other. So these 3 invariants, the last 3, and as I said, you can show. So at first, if you just work with the small quantum cohomology, you have that the cohomology of the K3 is sent to E lambda. But then if you deform, you know that you have to send the Jordan block to the Jordan block. And so you restrict you pass from H dot to H2. The K3, which is sent to the H4 of the Gushel-Mukai. And I think I'll stop.
Thank you very much. Are there any questions? About the deformation, so you compute it at some orders,
Mm-hmm.
and yeah. So what are the difficulties to just get the full matrix at deformation normality?
Wait. I would have answered time, but yeah, I mean, you need to do some more computations. You need to compute some invariants more. So it's but of course, time, because you have to stop at some order. You don't have anything that tells you probability invariance of I with many insertions. And also, yeah, so we compute the matrix at order 1. So when we deform, we don't know anymore if the eigenvalue is 0, but we don't know what it is. That's the reason why the result is holds for not with rational coefficients, but pure.
So what's important for you is like even like at order 1, you see that the Jordan block appears and
Yes.
not the 0 matrix anymore.
Yes. So yeah. So what we compute that the rank is 1 and cannot be bigger, but it's at least 1 at order 1. And then we say okay, but in so we will find a parameter t, let's say, for which the rank will be different from 0. and it will be concentrated in that part.
But in this case, you still define, right? Even if there is like a further splitting.
What?
In this case, in this very case, you still would define, right? If there is further splitting also, because okay, gonna get like a less Hodge classes, right? But you know that in each atom has to have at least one Hodge class, right?
Yeah, but here you know that you cannot split any further because.
Yeah, sure. I mean, so maybe this question about like sometimes you know where to stop, whether like keep iterating. This is about Jeremy, about where you like keep iterating the process of a computation. I mean, sometimes you're just lucky. I mean, because you know that each atom has to have one Hodge class, right?
Yeah, but you would be very not fine if they split.
Yeah, but I mean, so in this very case,
Yes, because if that splits for some deformation, that means that your atom is too small to contain a K3, and then it means that
you can always deform.
is irrational. But the coefficient of t square is constant equal to 1, even if there is further split, isn't it? In this case? The coefficient of t2 square in the Rothschild polynomial, even if this further split in this case, isn't this equal to 1 yet?
Yes. Yes.
And then it has to come from surface.
Yes, but I think what Jeremy is saying is that imagine that your things split when you certain Gushel-Mukai has this matrix that splits, then you can deform it back to. I mean, and I think you can do it. Just one should be a little bit precise, but you can deform it to a rational Gushel-Mukai where. So you have deformed along a class which was Hodge or in the F0 Hodge cohomology, and you can deform it so that it remains Hodge, and so you can deform it there. But there you know that there should exist a K3 because of the
yeah, sure. I mean, about the non-rationality, I think it's okay, but indeed, I don't think you can prove this Hasse type result. Yeah, because in so far rationality is sufficient to check that even if there's further splitting is not surface points or curves, right?
Yeah.
That's my point. But indeed, you cannot conclude that's K3, that I agree. Yeah, okay. Yes, for sure.
Any other questions? So if not, let's thank Vladimiro again. Of point genus 1 curves and logarithm of adequate numbers.
Thank you. Thank you for we thank the organizers for the invitation and thank you for the introduction. Yeah, so I'm going to talk about moduli spaces of pointed genus 1 curves in connection with a certain problem in number theory, which will have to do with logarithms of certain numbers. Okay. So before starting the actual talk, let me just say that all of this is joint work with Francis Brown at Oxford. I gave a very similar talk a little bit more than a year ago here at IMEC in the local center. It's a similar talk, except that at the time we didn't have the preprint yet, and also we didn't have some of the results that I present here today. So that's basically what changed. So we have this sort of very long preprint on this. Let's say this talk is a subset of the things we discussed in this preprint. And in this talk, I want to focus on basically 3 things. I'll recall what this Rosaghi conjecture is, which is sort of the problem that motivated the whole this whole project. I'll not spend too much time on that, but I'll just briefly say what it is. Let me also say that there's been, this is not a conjecture anymore, at least not in the way it was originally formulated. Very recently, there's been an analytic proof purely analytic proof of this conjecture. So what we're going to do here is that I'm going to try to look at this conjecture in a completely different way by relating it to the geometry of these moduli spaces and Manhã. And then I'll discuss some aspects of this connection. A very nice thing that comes out of our approach is that it actually motivates other problems, other purely geometric problems on N1N that, as far as we know, have not been formulated before. There's another direction, which is we can sort of see this Gross-Zagier conjecture in our approach as basically just a small part of a much larger set of problems in number theory, but I will not touch this aspect here in this talk. Okay? All right, so let me start with the Gross-Zagier conjecture very briefly, just to explain where it comes from. So to set up notation that I'm going to use throughout the talk, H is the upper half plane. So recall that the upper half plane has a natural action of this modular group SLT of Z by Mevius transformations. And sort of the starting point of this whole story is, let's say, Klein's J invariant. So this is a function defined by Klein. Actually, this picture I took from the paper of Klein. That is invariant under this action of SLT of Z. And actually, it induces an isomorphism. Right? If you mod out H by this group, it induces an isomorphism with C or with the affine line, right? So this picture here that Klein had in his paper is basically the fundamental domain. So the fundamental domain is one shaded area and one white area. And the shading corresponds to, like, if you see C into the Riemann sphere, the shading is basically the northern and the southern hemisphere of the Riemann sphere. Okay? So that's one of the most important properties of this Klein's J function. And then there's some normalization, and it's here the normalization. So J of this point is 1, J of this point is 0, and so on. Okay? Now, the interpretation of this result here, that this function identifies this quotient with C, is that this function is basically putting a coordinate on the moduli space of genus 1 curves with one marked point, which we also call elliptic curves. Okay? So actually this quotient here, you can identify with this moduli space of genus 1 curves with one marked point, because for any point in the upper half plane, you take, so this point is called Z, you take the lattice generated by 1 and Z, there's a lattice. Here, this is a fundamental parallelogram of this lattice. And then the quotient of C by this lattice is a torus. And for instance, the point 0 here determines marked point here, class of 0 in this case. Okay? So that's any point of H you can associate a genus 1 curve, so in algebraic geometry language, a genus 1 curve with one marked point, and then you can check that this is actually an isomorphism. Okay? So on the other hand, this is identifying this quotient with C, so you can think of this J as a coordinate that you put on this modular space and Manhã. Okay. All right, so this function J satisfies a lot of very surprising arithmetic properties. One of them is this theorem of Kronecker. I'm not really sure Kronecker proved this theorem, but anyway, he certainly stated it, which is this very strange property that this function, which is highly transcendental, But it takes, when you take z, this point in the overhead plane, to be a quadratic number, so satisfies a quadratic equation over the rationals, then the image of this point under this J invariant, so the value of this function, is an algebraic number. Okay, so and of course you don't expect this kind of properties for random transcendental functions. It's a very special property that this J invariant satisfies. So here is just an explicit example. So this was computed by Weber a long time ago. So for instance, J of square root of minus 14. So this is a quadratic number. Is this complicated algebraic number? Okay. So that's one of these arithmetic properties. There are many other that are of interest to number theorists and other people as well. This particular fact here, I'm highlighting this theorem of Kronecker. This has a geometric interpretation as follows. It's basically saying, I'm not going to explain this very much, but it's basically saying that whenever you have an elliptic curve or a complex torus with too many endomorphisms, so in general, if you have the complex torus, you can always multiply by an integer, right? Because multiplication by an integer preserves the lattice, so it's going to induce some endomorphism of the torus. But it happens that some complex tori, namely those determined exactly by these quadratic numbers, they have more endomorphisms than the others. So they have extra endomorphisms which are not multiplication by an integer. They are actually multiplication by a complex number that is not involved. Okay? So this fact here is saying that these complex tori with extra endomorphisms, they're actually defined over the algebraic numbers. So you can give an algebraic equation with algebraic coefficients for these terms. Okay? And this is because this function here determines the field of definition of the algebraic number. Okay? So these special points, which are just the quadratic numbers, in number theory they're called CM points. So do not confuse with Cohen-Macaulay. It's CM for complex multiplication. Okay? So this result is basically the starting point of this whole theory of complex multiplication, which was very popular at the end of the 19th century, and then it had a comeback later with the theory of complex multiplication of linear varieties and so on. And you know, in a sense, everything I'm going to say here also can be traced back to this theory of complex multiplication. Okay, so yeah, I just put here this phrase attributed to Hilbert. That he basically thought this was the most beautiful theory in mathematics, this complex multiplication theory. Okay, all right. So for us, what's going to be important is that in the 80s. Gross and Zagier published this highly influential paper in number theory. This paper here, which people just know as the Gross-Zagier paper. In this paper, so the most interesting thing that this paper does is that it proves a key case of the BSD conjecture. So that's why people got interested in that, and what is interesting about this this proof is that it's basically just a computation they do. It's not there's not much of an interpretation of what's happening. It's basically a very long computation, and this computation involves this Higher-Grings function, which is something that we're going to consider in a minute. Okay. So this Higher-Grings function are just some analytic functions, real analytic functions, defined by an explicit formula like this. So it's an infinite sum over elements of SLT of Z. involving, so this is Legendre's function of second kind, some kind of special function. And this has something to do with the hyperbolic distance between these two points, Z and gamma. Okay? So it's a function in two variables, Z and W. These two variables live in the half plane. They're not in the same orbit, otherwise this would have a singularity. And there's a parameter S as well. Okay? So for each S you have a higher Green's function. Okay? And these higher Green's functions, they're supposed to be generalizations of this Green's function here, which you can think of as a Green's function, the typical one, on the Riemann sphere with this coordinate j. Okay, so you think this j function has some coordinate, and then you're seeing this as a function on h on the upper half plane, or on two copies of the upper half plane, using this function j. Okay, so g1 would be this difference of this logarithm of this difference of the j invariants. Okay. But okay, so this function appears in the proof, but it's very unclear what it means. It's just given by some explicit formula. There are some analytic properties that are desirable that this function satisfies, but other than that, we don't have like an interpretation of what this function actually means. Okay. Okay, but then in the end of their paper, so this is not the main part of the paper, but in the end of the paper, since this function came up in their paper, they started to study it, and they realized that this function also satisfies some remarkable arithmetic properties. So what I'm going to state here is just for this particular S's here, 1, 2, 3, 4, 5, not 6, 7. But there's a statement for any integer S, positive integer S. Okay, it's just that for this particular S's, the statement is simpler, so that's what I'm going to do in this solve. Okay, so they realize that when S is an integer, and again you consider Z and W to be Cn points, then if you compute the value of this function, then you get some explicit algebraic number here. So this dz and dw are just the discriminants of the quadratic equations of z and w. So there's something, some kind of square root here. But then this is the main thing. It's the logarithm of an algebraic number. Okay. So when you compute this function on these special values, the same ones, the Cn values, the same points, you get this logarithm of an algebraic number. And of course, this generalizes what we know for, let's say, the classical Green's function, because the classical Green's function is just globally a logarithm of a difference of J invariants. And by Kronecker, we know that when you compute J invariants on algebraic numbers, you get, when you compute J invariants on quadratic numbers, you get algebraic numbers. So the value of this Green's function on Cn points will be the logarithm of an algebraic number. Okay. But the trouble is that these functions have that horrible definition that, and how can you prove that when you compute at these special values, then you get logarithm of an algebraic number. Okay. Well, this is just another explicit example. This one was computed by Anton Melic in his thesis. And so this problem generated a series of works. So Gross and Zagier, they thought about this problem. So there's this other paper of Gross and Zagier where they discuss some aspects of this problem. Then there's another very important paper of Zhang, very geometric. Then Melic, in his thesis, so Melic was a student of Tom Zagier. He sort of, his thesis is about this problem, also geometric, but very different from what we're going to discuss here. Then there's this series of analytic works. Wiazowska, she was also a student of Zagier. She also worked on this problem. And this series of works eventually culminated in this analytic proof that I mentioned in the first slide. Okay. But what I want to explain here is how to relate this conjecture, which seems a bit arbitrary. So you have this function, this crazy function, and you're saying that when you compute it on certain special values, you get logarithm of an algebraic number. So I want to sort of explain what's the geometry behind this conjecture. Okay? All right, so that's for the Gruszage conjecture. And now, as for the usual Green's function, the G1, you know it's related to, the Green's function involves J, this J invariant. And this J invariant, you know it's related to the moduli space of elliptic curves. It's not very hard to imagine that this more general Green's function will also be related to some moduli space of elliptic curves. And the moduli spaces that will appear in the story are these ones, moduli spaces of genus 1 curves with n marked points. Okay? So let me try to explain what we're going to do now. So this Q1, so the standard Green's function, so is a logarithm. And a logarithm, we know a logarithm is, you can think of it as an integral. Okay. In this particular case, it's the logarithm of an absolute value squared. So you can think of this as jz minus jw times its complex conjugate. So it's the sum of two integrals, right? And the integral explicitly is this one. So you're integrating this differential form dx over x minus j of w. So let's say I'm fixing w, and then I express my Green's function as this. Okay, so you can either think of this G1 as an integral, or you can think of it as a primitive, at least up to a constant. It's basically just some function that when you differentiate with respect to z, let's say w is fixed, you get this sum of, so this form of the third kind, let's say, so it has simple poles, plus its complex conjugate. Okay? So this new, I'm denoting here, is a one form of the third kind in the terminology, in the algebraic geometry terminology, on M11, which is this modular space, which I'm thinking with coordinates j. And it has poles at j of w. Okay? So the question is now, if I can do that for G1, can I do the same thing for this higher Green's function? So can I express my higher Green's function as some kind of integral or as some kind of primitive of some natural differential forms? Okay. So a little bit about these moduli spaces. M1n is the moduli space of genus 1 curve or complex tori with n marked points. Okay, so these points have an order and they are supposed to be distinct. Okay, and M1n bar is the usual compactification we consider in the theory, this Deligne-Montfort compactification, where you also admit not only smooth curves, but you also admit stable curves. Okay. So this moduli space, an important aspect of this moduli space is that you see there's a natural action of the symmetric group. Basically, you just permute the marked points on the complex order. Okay. And this action will appear in a moment, so we're going to actually use it. Just to be able to give concrete formulas, you can also describe this moduli space rather explicitly by analytically, so you can sort of uniformize the moduli space as follows. Basically, this U will be an open set, a certain open subset of H cross Cn minus 1. So this first point here in H will determine the elliptic curve with one marked point, which is 0. And the other points here will determine the other marked points. Okay, so the other elements of that. And this condition here is just to guarantee that these points will be distinct. Okay? So you have this open subset of H cross Cn minus 1, and then you do exactly what I said. So you map Z to this complex torus with the zero marked point, and you map the other points to the points they define in this complex torus. Okay? And then you can check that this is gamma 1n invariant, where this gamma 1n is this same direct product of SL2 of Z, which acts here, and then n-1 copies of Z2, which act on each one of these copies of C. Okay? So this is just to be able to give explicit formulas later in the talk. All right. Okay, so now what I'm going to do is that I'm going to define these differential forms. I'm going to give an explicit definition of these differential forms that I mentioned before, for which the Huygens function is supposed to be some kind of primitive of these differential forms. Okay, so now the formulas will be a bit cumbersome because what I'm presenting here is not exactly the way we did in the paper. I'm taking a shortcut to make it simpler. But anyway, this is the way I found to make it fit in the presentation. So I'm just going to give a brutal direct definition of these differential forms, and they're going to involve these functions here, these functions psi. Okay. So now I'm going to do the following for n, for any odd n, at least 3. And the fact that n is odd is just for this function to be non-zero. Otherwise, if it's even, everything is 0. Okay. And any p and q satisfying this, p plus q is n minus 1. I define some explicit function in 2 variables, z and w. It's only real analytic in w because it involves also complex conjugation in w, but it's analytic, complex analytic in Z, except that it has some singularity. So if you fix W, this is a meromorphic function in Z. And in fact, since I'm doing this sum here, this is going to be what we call a meromorphic modular form in Z. Okay. So that's the sort of the context that we actually work with in the paper. We work within this theory of modular forms. So these things become a bit more natural in this section. Okay? So once you define this function, we define this differential form nu pq, which is basically you take this sort of this top form here, dz wedge du1, etc., and you multiply by this function. Okay. So this nu PQ are going to be the analogs of the mu I showed before. Okay. And just one more notation. So let's define dW, so D for divisor, to be basically the fiber. So this M1N, it projects onto M11, basically by forgetting the last marked points. So just keep the first one. Okay. So there's this natural map here. And here at M11 you have a point determined by W, which is basically this point corresponding to the elliptic curve at W, defined by W. And dW is just the fiber of that. Okay, so it's the pre-image, the divisor above this one. Okay. So here's sort of a simplified version of a theorem in the paper. So this nu PQ, they all, so if I fix W, okay, I fix W and I'm seeing these functions as functions of Z only, okay? So they're gonna define algebraic N forms on this open subset of the modular space M1N bar. So M1N bar minus dW, so they're gonna have singularities along dW, which you can see by this explicit formula here. And so this has a natural algebraic structure, and these forms we can prove they're algebraic. And the cohomology classes are Sn alternating. So this means that if you apply the action of Sn, it comes out just a sign of the action. Okay. So it's the alternating part of the representation given by Sn if you add Sn on the differential forms. Okay. And actually, we can be much more precise about what these differential forms are doing in terms of the natural mixed Hodge structure that you have in this moduli space. So here I'm just writing, just to simplify. So you take the nth cohomology of this moduli space minus the divisor. This sign here is means that I'm just taking the alternating part of the cohomology. So the part of the cohomology that transforms as the sign character under the action of Sn. And this breaks down as sort of this pure part here, so the cohomology of the whole space, plus the space generated by these differential forms. Okay? And you can be more precise with the Hodge filtration and so on, but that's enough for what I'm at to state. All right? Okay, so the theorem is that this, now it's really quite cumbersome. In this notation, but it's not like this in paper, okay? So the theorem is that this, if you take these differential forms, nu pq, and sum it's the complex conjugate of nu qp, nu qp, right? Nu pq plus nu qp bar. These forms are exact, so they are the differential of some n-1 forms, this lowercase gpq. And this lowercase gpq, they have some kind of natural expansion in terms of other differential forms. And the functions that appear as coefficients are basically what we are also going to call Hayek-Green's functions. So they are this more general version of Hayek-Green's functions with extra indices here. They are basically coefficients, in some sense, of this primitive of this differential forms here of the third kind. Okay, and the expansion here I put it very explicitly, so you can define these one forms here. They don't look very algebraic. And then with these one forms, you can define these n-1 forms. They sort of degenerate the n-1 forms, and then you can write any guy as a combination of those. These are the functions that appear as coefficients. Okay? It's not very important, the precise form of these guys. It's just the fact that this, when you consider these differential forms and some primitive of that, there appears somewhat naturally these functions here. And these functions, they actually recover the Hayek-Green's function that Gross-Zagier considered. Actually, you can organize them in some kind of matrix, and in the central entry of this matrix, you find precisely this Hayek-Green's function that we started with. Okay, so in these expansions here, the central element is basically this Hayek-Green's function up to some other coefficients that are not very important. Okay? So to summarize, so given any odd n, at least 3, we find a whole matrix of Hayek-Green's functions, which appear as sort of coefficients of these n-1 forms here. We understand very precisely how they connect with sort of this cohomology group, and actually with the Hodge structure here, the mixed Hodge structure here. And the point is that this Green's function that appear in the Gross-Zagier conjecture is basically just one of these entries. It's basically the central entry. Okay, so in general we get this kind of matrices, and the function that appears in the conjecture is this one. But you also have all the others that have not been considered in other problems. All right. So now to sort of explain how to connect this with this problem, this Gauss-Argy problem, I need to talk a little bit about motives. So crash course on motives. Let me briefly explain what's the idea of a motive. One nice thing about this project is that in a lot of papers, motives are used more as a philosophy or as some kind of guiding direction to what you should prove. But here we actually need to use the actual theory of motives in our work. Okay? So very briefly, in algebraic varieties, in the theory of algebraic varieties, you have many different cohomology theories. Okay, so big K here is going to be a number field, so a field of algebraic numbers, finite extension of Q. And there are many different cohomology theories you can consider. So here I'm highlighting the important ones for this work, which is the Betti cohomology. So the Betti cohomology is just the usual singular cohomology. When you take your algebraic variety, you see that as a complex manifold. You compute the singular cohomology, and this we call the Betti cohomology. But it also has other cohomology theories. For instance, you have the algebraic de Rham cohomology, which is sort of similar to the usual de Rham cohomology using smooth forms, but you can define it just using algebraic forms with coefficient integer. And then you get another cohomology group, which is a K vector space. Okay. And you have other cohomology theories, so you have elliptic cohomology, crystalline cohomology, and so on and so on. Okay? And so, but for each one of these different cohomology theories, they come with different structures. So for instance, the Betti cohomology comes naturally with a complex conjugation, which has to do with complex conjugating the solutions of, so the rational points of your algebraic variety. The algebraic de Rham cohomology comes with Hodge filtration, and so on. So these cohomologies, they're different things, but you can compare them if you extend scalars to C. So there's an important theorem of Grothendieck saying that the algebraic de Rham cohomology actually computes the cohomology you expect, provided you extend scalars to C. So there's this comparison isomorphism where the de Rham cohomology, the algebraic de Rham cohomology, and the Betti cohomology are the same after extension of scalars. And the isomorphism is given explicitly by integration, just like the usual de Rham isomorphism, except that here you're always integrating some cohomology classes, which are algebraic differential forms with coefficients in algebraic numbers. And these particular integrals, we have a name for that, we call them periods. Okay, what's the motive of an algebraic variety? So the motive is some linear algebra object living in some category, okay? That it's basically some kind of cohomology, but it's a super general cohomology. It contains all possible cohomological information of X for all the cohomology theories. So all of these cohomology theories, the motive of X contains all of this information, all this complex conjugation, Hodge filtration, Dollar excitation, and so on. Okay? So it's basically some super cohomology theory that contains all possible cohomological information for all possible cohomology theories. Okay? The trouble with that is that it's not so easy to define what this actually is, what is the category you want to work with, and there are different theories that do slightly different things. So the theory that we're going to use is this Voevodsky's theory, which doesn't really construct an abelian category of motives, but constructs a triangulated category of motives that is morally supposed to be the derived category of the abelian category of motives. Okay, but this category, which is just a triangulated category, is good enough for many applications. Okay, so this is D and K. So this is a triangulated category of motives over K. Okay, so here I'm just stating some properties this category satisfies. So it's a Q linear category, triangulated, pseudo-abelian, so meaning that it's not a billion, but you have kernels of projectors, at least. And rigid tensor, meaning you have some tensor product and duality as well. Okay? So that's Webb-Wadsky's category, and there's a natural functor that takes any pair of algebraic varieties, so y a subalgebraic variety of x, and associates an object in this category which is supposed to be the relative cohomology of this pair. Okay, so that's the relative cohomology motive of the pair. Of course, if y is empty set, then this is just the absolute cohomology, so the cohomology of x. Okay. And now remember, this is a triangulated category, and so, for instance, this relative cohomology motive, it sits in the long exact sequence of relative cohomology. So here in this category, you think of that as some distinguished triangle in the category, so that behaves like the relative cohomology along the exact sequence. So this triangle mapping this relative cohomology to h of x and h of y with some shift in the degree is a sub of that. Okay. Now, how does this cohomology theory recovers how these motives recover the usual cohomology theories? The way we phrase that is in terms of realization functors. So we call them realization functors. So there are natural functors defined in this category of motives. So there's one for each cohomology, the cohomology theory. So there's a Betti realization, there is a Durand realization, and so on. Okay. So these functors, what they do is, if you take, for instance, the relative cohomology motive of a pair of algebraic varieties, and then you apply this functor, you recover the cohomology. Okay. So the concrete. So if you apply the Betti realization functor, you recover, for instance, the Betti cohomology of the pair, which is just a singular cohomology. If you apply the Durand realization functor, you recover the Durand cohomology, and so on. And then Grothendieck's theorem, you can rephrase it in terms of some natural isomorphism between these two functors after extension of scalars to C. Okay, so you can sort of upgrade Grothendieck's theorem to this natural isomorphism between these two functors. Okay, so this category of motives, yes.
I don't see any relation in the linearity like this. There is some sort of Grothendieck theorem related.
Yes, but it's way more complicated. But there is also like comparison isomorphisms relating L-area cohomology with other kinds of complex.
Okay.
And then you have all these very different notions of periods that appear in arithmetic geometry. But for us, we're just going to work with these two ones, which are most classical ones. Okay. All right. So some basic notation here that people use in the theory of motives. So the trivial motive, which is basically just the cohomology of a point, is denoted by Q0. Okay. The Lefschetz motive, which is basically this reduced cohomology of the punctured complex plane or punctured affine line, is denoted by Q of -1. And these Tate motives in general are just powers of the Lefschetz motive. So if it's a positive power, it's Q of -n. If it's a negative power, it's Q of n. Okay. So all of these are Tate motives. We call them Tate motives. And then there's this action of Tate twist, which is you just take a motive and you tensor with some Tate motive. And this Tate twist, sort of the reason it's important is because it has to do with pointer duality. Okay? So I'm not going to explain too much that, but it's a very important piece in the theory. Okay. But these guys, the Kummer motives are really the important objects for this talk. So the Kummer motives, they're basically a relative cohomology motive of the punctured, I'm going to do a drawing later, of the punctured complex plane, if you like, or the punctured affine line, relative to 2 points. I'm taking here 1 and 1/2. Okay. So these guys, using the relative cohomology sequence I showed in the previous slide, they sit in this distinguished triangle that you can think of as an extension, right? So this Kummer motive is an extension of this Q of minus 1 Lefschetz motive by Q of 0. Okay, so let me explain this more precisely.
Why do you need the shift in the definition of Lefschetz motive?
Here, it's just because I want, so this shift has to do with the cohomological degree. It's not very important, it's just because I want to put the degrees in the right places. Okay? But yeah, you can safely ignore all these shifts that I'm putting here. Okay, so the point is that these Kummer motives, what are the relation with the topic of this talk, is because the periods of Kummer motives, so these numbers that appear in this comparison isomorphism, they are basically logarithms of an algebraic number. Okay, that's how we think of logarithms of an algebraic number in algebraic geometry. They are periods of Kummer motives. Okay, that's the interpretation. So here I'm just drawing. So this is the relative homology of, you see, the punctured plane relative to 2 points 1 and alpha. So it has two. It's generated by two homology classes. One, this circle that turns around the origin, and another one is a path from 1 to alpha. Okay, so that gives the dual of the Betti realization. And the Durand realization is given by these explicit differential forms, the relative Durand cohomology. And if you compute the period matrix, you get, so the period matrix is basically just the matrix of the isomorphism, okay, in this basis. You get precisely, you get 1 log of alpha, 0, 2 pi I. Okay, so this log of alpha, it appears explicitly as some kind of period of this motive. Okay. Well, there's a variant of that, which we call the single-valued period matrix, which I'm not going to explain, which is basically you do some operation on this period matrix, and you get something else. And here, in particular, you get, instead of log of alpha, you get log of absolute value of alpha squared. So it's called single-valued because if you think log as a function, so the logarithm, the complex logarithm, is not a single-valued function, depending on the path of integration. And this sort of operation here kills this choice of the path of integration, and you obtain a single-valued function. So the log of absolute value is single-valued. Okay, so that's how you talk about. So now the main point, and I'm gonna end. I'm gonna walk to the end of the talk now, is that. Actually, so we've seen that these logarithms are periods of these Kummer motives, right? And these Kummer motives, they are extensions of this Lefschetz motive, Q of minus 1 by Q of 0. Okay? Now, it turns out that in the theory of Voevodsky, you can actually prove that every extension, so here I'm writing this extension like this abelian category notation, but in triangulated categories, it should be that. Okay? I prefer to think in terms of extensions. So every extension of Q of minus 1 by Q of 0 actually is a Kummer motive. Okay, comes from a Kummer motive. Okay. So that's the only way of producing extensions in this motives category of Q of minus 1 by Q of 0. So the upshot is the following: if you want to prove a number is a logarithm of an algebraic number. And so what you do is you write it as a period of some kind of motive, and then you try to understand, so for this motive in this category, you try to understand if inside this motive you can find some extension of Q of minus 1 by Q of 0. If you can do that, and of course you have to be careful with the weights and so on, but then you can prove your number is a logarithm, sorry, in this indirect way, in a geometric way. Okay. And that's exactly what we do. So now just to finish, putting everything together. Okay, so remember we saw that these higher-Green's functions have something to do with this moduli spaces M1 bar. Okay. Now I'm going to consider the following configuration. So here's M1 n bar projecting to M11. Okay, and remember we have these divisors, which are these fibers of the point determined by Z and the point determined by W. Okay. So I'm going to consider now the cohomology of M1n bar, and I'm going to delete the fiber at W, and I'm going to take the relative cohomology with respect to the fiber at Z. Okay? I take the alternating part, and then there's a shift which is you can ignore. Okay? And I take the alternating part because we saw that this alternating part has something to do with the differential forms. Okay, now the cohomology of these fibers I denote by F for fiber. Okay, just to give an notation. And I also take the alternating part. Okay. And of course, I do all of that in this category of motives. So I'm saying cohomology, but I should actually say motive. Okay? So now we have what we call a bi-extension. Okay. So here in this horizontal diagram here, so this is a distinguished triangle given by the relative cohomology along exact sequence. Okay, that I had before. Okay. And here, in this vertical triangle, is basically the Geising sequence, or the residual sequence. Okay, so that's another type of sequence that you always have for cohomology theories. You also have in this category of Voivodski motives. Okay, so basically from here to here, you consider the residue of the differential form at W or at this divisor. Okay. Now, so here you get this full cohomology of the whole moduli space, compactified moduli space, the alternating part. And you see that these are all distinguished triangles. So you can think of as short direct sequences. If this guy is 0, so you're saying that this arrow is an isomorphism. Okay? And then you have an extension, one extension, not a bi-extension, an actual extension of this motive by this motive. Okay? And you can see it's already quite similar to the thing Kummer motives satisfy. Okay? But this is under this hypothesis that this cohomology is 0. Okay? Okay. So here's sort of the main theorems. So here, this is just to remember it, so we can read the theorem. So I'm putting together a lot of different statements. Okay? So the first statement is that this G, P, Q, RS, which are these higher-Green's functions that we discussed before. So remember, we saw them as some kind of primitives of differential forms. With a bit more work, you can prove there are periods of these motives. Okay? So there are some integrals of differential forms that appear in these motives. Okay? So that's the interpretation of these higher-Green's functions. They are just periods of these motives of these moduli spaces. Okay? Well, it turns out that these fiber motives here, okay, which is the cohomology of these fibers, you can relate them to the cohomology just of the corresponding elliptic curve, so the symmetric power of the cohomology of the elliptic curve. And what happens when the elliptic curve is Cn, so everything I said until now is super general, but if the elliptic curve is Cn, remember it has extra endomorphisms, and with these extra endomorphisms, you can use them to split this cohomology into some Tate part plus something else. Okay? But now you see there's some Tate part here and there's some Tate part here. And then you can get a sub-extension of this extension, or a sub-quotient of this extension. You do some push and pull thing, where you just cut out these Tate parts. And then you get, as a sub-quotient of your original motive, some extension of these Tate motives. This is all under this hypothesis that this motive is 0, so we can actually get a simple extension. Okay. But now you do some tape twist here, you get exactly, precisely an extension of Q minus 1 by Q of 0. So, and we know that every extension like this is a cohomology, and because it's a cohomology, its period is a logarithm, but then its period is also some Huygens function like here, and by weight reasons you can see it's exactly the middle piece, okay? And that's how you prove under this hypothesis that this guy is a logarithm, okay, with no details, of course. So just to finish then, well, okay, so this gives some proof conditional to this property. Okay. Now this is an actual big problem because this is a vanishing thing you have to prove about motives, and these are not very easy in general. So what we do know is that for the S's I mentioned in the beginning of the talk, okay, we know that the actual cohomology, if you compute the cohomology, so the alternating part of this cohomology, for instance, the Betti cohomology, this is actually 0. This vanishes. Okay, and this follows from a theorem of Faber and Consani and the classical theory of modular forms. Okay, and we expect that this automatically implies that the motive is 0. So there's a very famous conjecture in the theory of motives that we thought was proven some years ago, but it turns out it was not, which is the conservativity conjecture, basically saying that this functor, this realization functor, is conservative. So this means that if you can prove the cohomology 0, this would mean that if you could prove the cohomology 0, then the motive is automatically 0. Okay? But we don't know this conjecture. But what this argument proves until now is that, well, the Gross-Hagen conjecture, it reduces the Gross-Hagen conjecture to some vanishing statement on the theory of motives. Okay? This is already quite surprising. So the problem is we don't know how to prove this in general. Okay? But we do know in some particular cases. Okay? And it turns out you can still prove this motive is 0 in some cases if you prove something geometric about this moduli spaces. Okay? So one case we know the conservativity conjecture is when your motive is mixed state type. Okay? Doesn't matter what this is. You can think of as well in terms of the Voevodsky category. It's given by some iterated extension of tape motives. Okay? But geometrically, it's basically a mixed state motive is something you obtain usually by sort of cut and paste constructions using projective spaces. Okay, so the cohomology is constructed out of cohomology of projective space.
Okay, so it could also be thought as the cohomology of a quasi-projective, all right?
No, so I mean this cohomology is sort of a piece of the cohomology of a quasi-projective variety, of a projective variety. Or it's actually a stack in the small cases, but but then this mixed state property is saying basically that this space you can sort of construct it out of this cut and paste relations using projective spaces. It's not exactly that, but that's an intuitive way of thinking about what mixed state means more geometrically. Okay. So, and just to show this approach actually works, we prove in the paper that the first non-trivial case, which would be for n13, this motive is actually mixed state. Okay, so this is, and the proof is a very geometric construction, explicit, and so because the conservativity conjecture is known for mixed state motives, this fact implies that the motive is actually 0. And this gives a completely geometric and motivic proof of this conjecture in this case. Okay. We haven't really attempted to generalize this, but we do expect up to n less or equal to 10. So we haven't seen this problem formulated elsewhere, but we do expect these motives are all mixed state. Okay. And it's interesting to note that these spaces here, M1N, their geometric properties have been studied before. There's a classical result by Belarusky. So Belarusky proved in his thesis in the 90s that exactly for these values of n, these motifs M1N, these spaces M1N are rational. Okay, and rational, it has some sort of similar flavor to being mixed state, but it's not at all the same thing. Okay. But this is another problem, okay? So we do know they are rational, but this doesn't prove they're mixed state, okay? But we actually think they're all mixed state for n up until 10, and we know they're not for n greater or equal to 11. But I'm gonna stop here.
Are there any questions? So about n equals 11, this, there is like famously a non-zero 11 degree class on the M111. That is like the first non-tautological class that was found. Is this class in the thing with the sign? I mean, I don't remember what the sign means, but is it part of this or not?
Yeah, so from the point of view of differential form, so what basically you do is you can construct an explicit differential form which will be alternating just as we had before. And this differential form comes from a cusp form, so it's modular form of way 2. And then you can prove it's in this alternating part, and just for the fact that there's this non-trivial differential form, it's non-rational.
But then it means that this guy in red up there, this is non-zero for n equals 11, right?
Yes,
And
precisely. And so
the conjecture is not proven then in that case.
So the conjecture is different in that case. So these are the cases that I omitted. Okay, so in that case, you actually have to, in the original conjecture, you modify the function, you do some linear combination of that, and this linear combination, what it's doing motivically, is actually killing this motif here. Okay, but then you have to prove another thing. But that's the interpretation. So in the original conjecture, it's not a conjecture exactly about the value of the Huygens function. It's a conjecture about some linear combination of that. And the interpretation of that is that this linear combination, precisely what it does, is that it should kill this motif. And that's why you get, again, a simple extension, and you can repeat this argument, and you get a convergent extension.
Okay. And so this conjecture is about showing that something is the logarithm of an algebraic number. And at some point you talked about number fields, and do you have any control about in your theorem? Do you have any control about in which extension or which degree?
Yes, we basically it should be the same. Well, it should be. It is the same. So remember. Right in the beginning, we have this theorem of Kronecker. It should be basically the same number field generated by this J of. And this also have, so the theorem is actually much more precise than that. We know exactly what the degree of that is. It's the class number of whatever. It's something number theoretic. And in the Gross-Zagier conjecture, it's basically going to be, so you take the compositum of the field generated by J of Z, J of W, and that's basically it.
Okay. Any other questions? So let's thank you again.